Hey guys, just putting together a video for tonight's class. We will be reviewing for our midterm exam. This video will be part of your attendance for the night, along with in-house lab at some point tonight in the classroom. So in order for you to get attendance credit for this class, this video must be watched, and there will be a small quiz based on whether or not you actually watched this video. If you do not fill that quiz out, you will not get credit for tonight's class. So let us begin as we talk through this semester so far in review for our midterm. Your midterm will be next week, Tuesday, I believe it's March 9th. That will be your midterm exam for this semester. All right, let's begin. Second year, apprenticeship. Lesson 219, we started talking about three-phase power generation, transmission, and distribution, as well as an introduction to three-phase Ohm's law. Out of lesson 219, where I would definitely focus your studies on is that three-phase Ohm's law, the three-phase Ohm's law formulas. Now, on the CMS and in class, I have both given you a handout for a list of three-phase formulas. You will be allowed to use that handout, so I encourage you to find it, but I also encourage you to get these formulas written down in your notes as well, so you can identify which formula is used for what. Let's look at some three-phase formula, or three-phase Ohm's law. Many three-phase generators can be connected to deliver various output voltages. Guys, for your exam as well, you will need to be able to identify the differences between a delta and a Y transformer. Here's a couple examples right here on the screen. Know the differences, know their calculations and their formulas. We'll get to that here in a little bit, but just keep in mind you will need to understand the differences and the calculations involved with delta and Y three-phase transformers. Guys, whenever I use the term line voltage in regards to three-phase transformers, I'm referring to the line-to-line voltage. So if you hear the term line voltage, what's the line voltage of this transformer? Well, gee, that is the line-to-line voltage. So whatever the source, three-phase power consists of three outputs. You cannot have a three-phase circuit without three ungrounded conductors. Keep that in mind. I'm going to repeat it for those who are in the back. You cannot have a three-phase circuit without three ungrounded conductors. If you have less than three ungrounded conductors, you have a single-phase circuit. It does not matter whether or not it's coming from a three-phase panel board or not. Three ungrounded conductors are required for it to be three-phase. Anything less would be considered single-phase. And again, the line voltage is line-to-line, hot-to-hot, ungrounded to ungrounded voltage. That's when I'm referring to line voltage. Line to neutral voltage is completely different. So when you hear the term line voltage, it's not referring to that. It's only referring to line-to-line voltage. Know your voltage systems. We've talked about three-phase circuits majority of this semester. This here is a three-wire single-phase circuit or system. You notice that it's a 12240 single-phase three-wire system. That's your typical residence dwelling unit system. What I'm going to be talking about more so are these three-phase systems. A 12208 three-phase four-wire system. The line voltage would be 208. The line to neutral voltage would be 120. And that would be a Y system. And we'll get into that here in a little bit. As well as the 277 480 three-phase four-wire system. This line voltage would be 480. Its line to neutral voltage would be 277, and that also would be a Y system. And again, we'll get into the reasons behind that in a little bit. This right here, a 12240 volt three-phase four-wire system, is actually a delta. It is a delta high leg, and you will note that its line voltage is 240, but it has two other voltages to ground, or two other line to ground voltages, line to neutral. On the A and C phase, it has 120 volts, and on the B phase, it's 208. That is known as the high leg. I've heard in other areas, believe like Colorado, they call it the stinger. I've never heard that here in Indiana, but I know other places have slang for it, calling it the stinger, the high leg. That is going to have 208 volts to ground, and that high leg is unusable when it comes to single pole breaker operation. Know your general terms for transformers. What's your primary side? Primary side is where the voltage comes into the transformer to either be stepped up or stepped down. In the example on the screen, it's a step down. That's generally the case when it comes to transformers. We're generally stepping our voltage down more so than we are stepping it up. We will have that from occasion to occasion, but generally speaking, this is more common. The secondary conductors are on what you would consider the load side of the transformer. It's not really a line and load like you understand a disconnect, but it would be similar in its properties. Three-phase Ohm's law. Now, if you don't have an Ohm's law wheel or don't have Ohm's law notes regarding the general Ohm's law formulas, then I highly suggest you get those written down in your notes. For three-phase Ohm's law, it's a little bit different than just our standard single-phase Ohm's law. Our three-phase Ohm's law is requiring us to incorporate the square root of 3. Now we incorporate the square root of 3 because all three of our three-phase voltages are not in phase with each other, so we can't just add them up. A phase is started well before B phase and well before C phase, and once A phase has reached its peak, B phase is just about ready to climb, and so on and so forth. So we can't just add our voltages up with three-phase power. So we have to multiply our voltage by the square root of 3. You'll note here, as we have a three-phase formula, we're sizing for the overall amperage of a three-phase generator here. The I of L, or the I of line, equals the power of three-phase divided by E. I equals P divided by E. That formula stayed the same. However, we have to now incorporate the square root of 3. Guys, you wouldn't believe how many Ohm's law formulas you're going to see on this test. If anything, I would definitely camp out in understanding three-phase Ohm's law formulas. Go back, work on your homework a little bit from lesson 219, lesson 220, 221. You'll need to be familiar with three-phase Ohm's law and incorporating the square root of 3. Again, with the three-phase Ohm's law, you'll note here that we're trying to determine what's the power of our three-phase load. We take the I of line, multiply it by the E of line, incorporate the square root of 3. It's still P equals I times E. Ohm's law doesn't change, but in order to make it accurate, we have to include the square root of 3. So 36 amps times 243 phase, so 240 times the square root of 3 equals out to 15,000 watts, or 15 kW if your question is asking for kilowatts. So remember, incorporate the square root of 3. Go back and look at your formula sheets. Be prepared in that way. More terminology for you. When I talk about line current, or if the question's asking about line current, this is the current flowing in the circuit conductors, not the windings of your transformer. And it's represented by I line or IL. This is referring to the circuit conductors and not the winding. Now, when we're talking about the winding itself, or the coil inside the transformer, this is called coil current or winding current, and it's represented with an I coil or I winding in the formula. Yes, at times these will be different numbers compared to each other. depending whether it's in a delta or a Y configuration. So be familiar with the terminology here. Same with voltage. The voltage in the circuit conductors is designated as line voltage and represented by E line or EL. This is again the circuit conductor voltage, not necessarily the winding voltage. And then the voltage across a winding or the coil inside the transformer, whether it's the primary or the secondary, is known as coil voltage or winding voltage. And this is represented with an E coil or E winding in the question or in the formula. So again, know the differences here between the terminology. They will at times not be the same mathematically. Common transformer installs. Delta primaries are your most common when it comes to transformer installs. So be aware of that. Three-phase transformer banks. If my three-phase transformer bank is equally rated, a three-phase transformer bank is simply put 3 single-phase transformers added together. I have 3 single-phase transformers in conjunction with each other to create this three-phase circuit or system. And if all 3 of those transformers are banked rated equally, you can just add them together. So P of one phase plus P of one phase plus P of one phase equals your P of 3 phase in an equally balanced transformer bank. Getting into lesson 220, you're going to need to understand your deltas. What your different delta systems may be, understanding their voltage ratings, and the current and power calculations when it comes to the three-phase Ohm's law and a delta configuration. As with primaries, a transformer secondary can be connected in delta or Y. Right now I'm going to talk about delta, and this delta connection requires that the single-phase transformers each be interconnected so that X1 of one transformer is connected to the X2 of the next, and so on and so forth. So you see that the X1 of transformer 2 here is connected to the X2 of transformer 1, and its X1 is connected to the X2 of transformer 3, and its X1 is connected to X2 of transformer 2, and we have a series loop here. This is a series loop, or what would be considered just a delta transformer. And we've tapped off of each corner of this loop for our three-phase conductors. Now, when working on three-phase transformers, you've heard it mentioned that you have taps on the primary side that can be altered to change the turn ratio from a greater turn ratio to a lesser turn ratio. Remember, transformers based solely on induction, yes, but they're also based on the fact that the turn ratio is what it is. So if I've got a 480 volt primary and I want to step it down to a 120 volt secondary, I need a transformer that has a turn ratio of 4:1. For every secondary turn, I have 4 primary turns in that scenario. So understanding your turn ratio is going to be important. Understanding when you move your taps to change the turn ratio when you have a greater than expected or a lesser than expected voltage on the primary. And moving these taps will actually change the number of turns. So you see right here these little tabs sticking off the transformer winding. Those are the loops or the taps that we would need to change. Right now they're factory set in this drawing so that the input voltage would be exactly 480. But if we had an input voltage that was closer to 500, we would move these taps all the way to tap number 1, which is down here. I'd move this tap from tap number 3 to tap number 1, tap number 3 to tap number 1, so that my turn ratio would change, allowing me to still get 120 volts on the secondary side. Ungrounded three-phase deltas. Understand the makeup and characters of a three-phase, three-wire delta. With an ungrounded delta, your voltage to ground theoretically would be 0 because there's no grounded wire or grounded circuit conductor involved in that transformer. Now, there will be requirements for there to be ground detectors according to the NEC, but that is not necessarily used as a grounded conductor. So the voltage to ground would theoretically be 0 in a 3-phase, 3-wire ungrounded delta. In a corner grounded delta, also known as the dead man's leg, will give you a misleading voltage to ground reading at times. On a 3-phase, 3-wire delta, a corner grounded system, all but one phase to ground would read 240 if it was a 240 delta. The third phase, or the C phase, if you had corner grounded the C phase, would actually read 0 volts to ground, making the dead man think that the system was de-energized, he'd do his work and get the shock of his life. So this was known as a corner grounded delta. So when you're taking readings on any kind of delta system, always use your meter and go phase to phase on all 3, and then phase to ground on all 3. And this will identify whether it's an ungrounded delta, a delta high leg, or a corner grounded delta. In delta transformers, the coil voltage is the same as the line-to-line voltage in a delta transformer. So this means that the E of line equals the E of coil in a delta system. I would definitely put that in my notes if I were you. You will see this brought up multiple times on the exam. Also, with the coil current versus line current in a delta transformer, coil current is off by the square root of 3 from line current. Now, you're probably saying, what the heck does that mean? Why is it off by the square root of 3? Well, what I mean by that is, if you look at the formulas below this, I line of delta equals the square root of 3 times the coil of I coil of delta. That means if I'm looking for my I of line and I know what my I of coil may be, I multiply the I of coil by the square root of 3 in order to figure out my I of line. Or vice versa. If I'm trying to figure out what the coil amperage might be, and I know what the line amperage is, I take that line amperage, divide it by the square root of 3 to figure out what my coil amperage is in a delta system. Voltage is constant. Amperage is off by the square root of 3. And again, here's some more formulas for you to make sure you have in your notes for 3-phase power, 3-phase Ohm's law. Power of 3-phase equals the square root of 3 times the amperage of line times the voltage of line. Remember, in a transformer, power in equals power out. And then the formula for coil current, right at the bottom there, the amperage of the coil primary is equal to the rated, or the I coil, I'm not rated, I'm sorry, the I coil secondary times the E coil of secondary divided by the E coil primary. That's supposed to say primary right there. Moving on up. This 3-phase 4-wire grounded system is known as the delta high leg. This is an example of a delta high leg here. You'll note that we have a neutral conductor on the center tap of transformer number 3. Because we have that neutral on the center tap of transformer number 3, we have 3 separate voltages allowed by this system. Only 2 of which we are allowed to use when it comes to utilizing it for equipment. The center tap being right here on transformer 3, going to our neutral, means that anything between C phase and neutral would be 120. A phase and neutral would be 120. B phase, because it originates all the way over here and it's got a winding and a half before it reaches that center tap, and its series difference would be 208. And if I were to take a measurement between B and A, it would be 240. Between A and C, it would be 240. And between C and B, it would be 240, because this is still a 240 delta configuration. We've just added a fourth conductor and grounded it. Again, here's a representation of what I just said. The line voltage would be 240. The line to neutral voltage would be 120 or 208, depending on what phase you were measuring. And then your coil voltage would be 240 volts, measured between X1 and X2 on any transformer. Variation of three-phase, three-wire system utilizes only two transformers. This is known as an open delta. This is an open delta transformer system. It only uses two transformers. The only difference between an open delta and a closed delta, well, the only significant difference, the big difference, is that an open delta has less power available than a closed delta. Its kVA rating will be less, but it is still a three-phase transformer, a three-phase system utilizing only two single-phase transformers, known as an open delta. Now, 221, getting into our Y configurations. Yes, you will need to know the differences between delta and Y and all of their rules or formulas involved. So again, write down the formulas from your notes. Make sure you have them with you. A Y connection requires that the single-phase transformers be interconnected, so X1s and X2s of all three transformers are connected together. That's X1s or X2s. In the drawing here, it shows that all the X2s are interconnected together, and that's where the neutral is tapped on and grounded. They're giving us our grounded conductor, our neutral conductor. The NEC does not specify whether it's X1s or X2s, so that's really up to the installer or the manufacturer. Three-phase power transformer banks with Y-connected secondaries consist of three equally rated single-phase transformers. Now, one thing that I did not go over in delta, and I could actually back up here a little bit here. Well, I can't with my notes, but when with a delta, they don't always have to be equally rated. Oftentimes, there's what's called a lighting transformer, and then two power transformers. The two power transformers, in conjunction with the lighting transformer, take care of all the kVA requirements for the three-phase loads, and then the lighting transformer takes care of all the requirements for the 120 or 240 single-phase loads, depending on what requirements are in the building. So that would be a lighting transformer. In your worksheet or handout that I've given you, there are formulas for sizing lighting transformers. There are formulas for sizing lighting transformers. You will need to be familiar with those formulas and how to use them. So go back, look at your notes, identify how to size a lighting transformer. That was found in lesson 220. When it comes to our Y transformers in lesson 221, they are not allowed to be sized differently. You're going to have all equally rated. For a Y configuration, here's some formulas for you to use for your three-phase Ohm's law, as well as Y versus delta configurations. In a Y configuration, the coil amperage is constant with the line amperage. The line and coil amperage are the same. I line equals I coil. This is only for a Y configuration when calculating your amperage. And for voltage in a Y configuration, remember how in a delta our amperage was off by the square root of 3? It's very similar here for voltage in a Y configuration. Our voltage is off by the square root of 3, meaning that if I was trying to figure out what my line voltage is, and I know what my coil voltage is, I simply multiply the coil voltage by the square root of 3 to determine what my line voltage is. And vice versa. If I'm looking for my coil voltage and I know what my line voltage is, I take that line voltage and divide it by the square root of 3 to figure out what my coil voltage is. So for example, if my coil voltage is, let's see here, E coil equals 120, and I want to know what my E line is, I take my E coil, or 120, and I multiply it by the square root of 3, or 1.732. That gives me a voltage of roughly 208 volts. So this Y configuration would be a 120-208 three-phase Y system. Again, bringing back to turn ratios. Turn ratios are very important. Not only do they help us understand the transformation of voltage, but it also can be used to determine what the transformation of amperage would be. For example, if I have a 4-to-1 transformer, that means its voltage rating is 4-to-1, or voltage ratio is 4-to-1. To determine my amperage ratio, I simply flip that. So instead of a 4-to-1 voltage ratio, because I have a 4-to-1 voltage ratio, I would then have a 1-to-4 amperage ratio. So that being said, for an example like this, if my transformer was a 4-to-1 ratio, say it's a 480 to 120 transformer, and the secondary carries 20 amps. That's my secondary. How many amps would be on my primary? If I have a 20 amp secondary, my voltage ratio is 4-to-1, what would be my primary amperage? I would simply take that 20 amps and divide it by 4. It's a 4-to-1 ratio. So for every 4 amps on my secondary, I will have 1 amp on the primary. So 20 divided by 4, 5 amps. I would have 5 amps on my secondary. Or I'm sorry, on my primary. Again, a 4-to-1 ratio. If a voltage higher than the rated voltage is applied to the primary, then that rated secondary voltage will be delivered to a load, and that rated secondary voltage would be higher than the rated secondary voltage. If a voltage is higher on the in, it's going to be higher on the out. It's the best way to put it. So the formula for determining our actual secondary voltage would be to take our E of actual secondary, which is what we're looking for. It's going to be equal to our rated secondary divided by our rated primary. So if I had a 480 to 120 volt transformer, I put 480 here, 120 here, divide them, take that answer, and multiply it by the actual primary. Now if my actual primary was, let's say, 500, not 480, what would my actual secondary be? Well, then I would just take 120 and divide it by 480. I'll do that right now, which would give me 0.25. Then I multiply that by 500, which would give me an actual secondary of 125. Instead of the 120 I was expecting, I ended up with 125 because I had a higher than rated input or primary into this transformer. You will see questions like that on the quiz or the test. 222, nonlinear loads, three-phase fault currents and voltage drop. We will touch base on all three of these in the exam. You'll need to be aware of nonlinear loads. What is a nonlinear load? A nonlinear load produces high levels of harmonic currents. Examples of these nonlinear loads would be HID lighting, variable frequency drives, power chargers for a computer, phone chargers produce a nonlinear load. It's smaller, but it still produces one. Ballast, fluorescent lighting, all of these are examples of nonlinear loads. Computer servers. Now, these nonlinear loads create high levels of harmonic currents, and these harmonic currents can actually have an effect on the neutral, which is why a nonlinear load isolation transformer or a K-rated transformer can have neutrals twice the size of a normal transformer to be able to withstand that kind of ampacity. Again, these nonlinear loads, they produce current waveforms that do not conform to the waveform of the applied voltage. In many cases, this becomes additive upon the neutral, especially in a Y configuration, which is where nonlinear loads are actually more of a problem. You don't have any problems with nonlinear loads in a delta configuration because the waveforms are not additive. They would be more so just actually the term for it is they're trapped in the delta configuration and dissipated. Short circuits for three-phase versus single-phase. We've talked briefly about single-phase last semester. I of short circuit equals volt amps divided by the E of line times the Z of the circuit or the apparatus or the transformer. For a three-phase short circuit fault current or bolted current, the formula is very similar. So you're going to use the I of SC or I of short circuit that equals to the volt amps divided by the voltage times the square root of 3 because it's a three-phase circuit, and then you're also going to multiply it by the decimal form of Z. So for example, and I'm going to draw this out here, let's say I have a three-phase transformer 208 three-phase, and it's rated at 50,000 or 50 kVA. And it's the impedance rating on the transformer itself was 1.5%. What would be my available fault current if I were to short this out? So I take 208, multiply it by the square root of 3, multiply it by 1.5%. That's for one portion of this. And then I have 50 kVA divided by that answer. So let's write it out so it makes a little bit more sense. I've got my 50 kVA or my 50,000 divided by my 208 times the square root of 3. Sorry for my handwriting. Times the 1.5%, or in its decimal form, 0.0. That should be a 0. There it is. 0.015. Multiply all that together. 208. 50,000 divided by 208 times 1.732 times 0.015, I would have an available fault current of 9,253 amps. That's a lot of amps available to fault out at that three-phase circuit. So that's how you would calculate a three-phase short circuit, and similar to your single-phase short circuit. For voltage drop, you will be required to know voltage drop formulas. Voltage drop for three-phase is just a little bit different than voltage drop for single-phase. Remember, voltage drop for single-phase was 2 times kil times divided by the CMA, 2 kil over CMA. For three-phase circuits, it's square root of 3 kil over CMA, or square root of 3 times K times I times L. Formulas to keep in mind for voltage drop or to have in your notes. For a single-phase voltage drop formula, volts dropped equals 2 kil over CMA. Or if you're looking for the wire size, it's CMA equals 2 kil over voltage drop, or volts dropped. For three-phase voltage drop formulas, it's VD, or volts dropped three-phase, equals square root of 3 kil over CMA. Or if you're looking for the wire size, it's going to be CMA equals square root of 3 kil over volts dropped. And then also, unless noted otherwise, when it comes to K, it's going to be the R per foot times the CMA, unless the question tells you, hey, use 10.86 for K, or use 12.2 for K, or whatever the question may ask you. Otherwise noted, this would be the formula here for K. 223, identifying the NEC requirements. You're going to have some code lookup questions for transformer vaults, for transformer installation code articles for transformers are mostly found in Article 450. Article 450 for transformers. When it comes to transformers, temperature rise is how much heat above the ambient temperature an electrical component produces. So if I've got a NEMA class 105 transformer, its temperature rises at least 55 degrees above ambient temperature. Now this NEMA class 105 transformer would have to consider the ambient temperature of 40 degrees. It's assuming that you're installing the transformer in a 40 degrees Celsius location, and that it has a hot spot, or an average of 10 degrees Celsius between the hottest winding in the transformer and ambient temperature. Adding all those together, 40 plus 10 plus 55 would give a class rating of 105. And now that's just the class rating. The temperature rise of that transformer would be 55 degrees Celsius. That is, again, how much heat above the ambient temperature an electrical component produces, is temperature rise. For transformer installation, one thing you'll need to know is your type 1 versus type 2 buildings. A type 1 building has a fire resistance rating of 0 to 4 hours. A type 2 building only has a fire resistance rating of 0 to 2 hours. All that is based on the materials used in that building, whether they're combustible or less combustible. Doorways, fire exit hardware, talking about that specifically. Doorways for transformer vaults are mandatory to have fire exit hardware. This used to be called panic hardware, but now it's called fire exit hardware, installed so that if there's an emergency, you're able to get out of that transformer vault in a hurry. It acts as a push bar to open the door for you. Again, these doorways are actually designed so they have to be swinging away from the transformer vault, not into the transformer vault. They can never be, you never should be able to have to pull a door into a transformer vault to leave. It's always push to get out. But Article 450.41, 42, 43, and 45, all requirements for transformer volts. I would be familiar with those code references. Sizing of overcurrent protection for transformers. We're going to use section 450.3. 450.3a for over 1,000 volts nominal, based on location and based on primary versus secondary protection. That table looks very similar to this. You will use this table to calculate just how much more percentage of amps your protection needs to be than the equipment itself. So that being said, if I have a transformer and its primary is over 1,000 volts, so let's say it's a 4,000 volt transformer, the primary 4,160 volts, I do the math and I figure out that my primary is capable of handling up to 100 amps. And it has a Z or impedance factor of, I don't know, 2.2. That means I'm going to use the column here for primary protection over 1,000 volts. And let's say we're going to give it a fuse, not a circuit breaker. So I'm going to use the fuse rating column, and I need to line it up with, is this supervised location? And I did not say, so it's not a supervised location. So it would fall under any location. Then I would use either row not more than 6% impedance or more than 6%, not more than 10% impedance. I said our impedance was 2.2%, so I'm going to use this row here. I have a fuse rating that follows up with, it's an any location transformer, it's over 1,000 volts, and its impedance is less than 6%. I'm going to add 300% to that 100 amps that my transformer is capable of. If my transformer was capable of 100 amps on the primary, I have to multiply that 100 amps by 300% when I size my primary protection breaker fuse, in this case, protecting that transformer. So that's table 450.3a. That's for over 1,000 volts. If it's under 1,000 volts, 1,000 volts nominal or less, you're going to use table 450.3b. Primary, you're going to use table 450.3b. For primary and secondary protection, 450.3b as well. And then for transformer and feeder taps, you're going to reference Article 240. Article 240 has different references for transformer secondaries. But for sizing your primary protection, you're going to use this table here. Primary protection and secondary protection, use this table here. Now, one thing to note is note number 1. Note number 1 says where 125% of the current does not correspond to a standard rating or fuse or non-adjustable circuit breaker, a higher rating is permitted. That only applies to if I've only multiplied my overall current by 125%. And that only applies to transformers that have currents of 9 amps or more. If my transformer has a current of, let's say, 6 amps, I would use this column, and I would size it by 167%, which is more than my 125%. So if I've sized it according to my 167%, and I reach a non-standard size breaker, let's say it comes to 43 amps. At that case, according to note number 1, I cannot round it up to 50 amps. I have to round it down to 40. That's if I used this column or if I used this column. But if I used this column where it's only 125% for primary protection only, then I could round it up and it still came to 43 amps. I could then round it up to the next standard size, which I believe is 50. according to 240.6a. Unless there's a 45 in there that I'm not aware of, but I'm pretty sure it's 50. So know your notes, know your application. You will see a couple questions involving this. Section 240, like I talked about, addresses where overcurrent protection is required in circuits. Section 241.21c addresses minimum size transformer secondary conductors. 240.21c, transformer secondary conductor sizes. 240.21c2 is referred to as 10 feet secondary conductors, or the 10-foot rule for secondary conductors. That means that my secondary conductors are 10 feet or less. I would apply 240.21c2. If my transformer secondary conductors are 25 feet or less, then I use 240.21c6. And to take what they say in those codes and put it into just mathematical formula, if I have a 10-foot conductor, a secondary conductor, its minimum ampacity would be calculated using this formula. If I have a 25-foot or less transformer secondary conductor, its minimum ampacity would be calculated using this formula. Now, and I want you to pay close attention to this because this is where it can get sticky. That's the bare minimum just according to the secondary of the transformer. Now, let's say we've done our calculations here, and I determined that my smallest wire I can run on my transformer secondary is only a 60 amp wire because I've done all of my math involved. Yet, if I'm taking that secondary conductor and I'm feeding a main panel board or main breaker board, and that main breaker is sized at 200, I cannot run 60 amp wire. 60 amp wire is a bare minimum according to this, but in the same code it says it has to be able to be sized large enough to carry the load it's serving. And if it's serving a 200 amp load, then I need to have at least a 200 amp wire on that secondary. Even though this said it could be 60 amp, the load demands it be 200 amp. I always go with the greater of the two. So calculate your load and then calculate your minimum ampacity using these two formulas. Compare the two and go with the greater. If that doesn't make sense, rewind, play it over again, work through some of the problems found at the end of 223.5. Buck boost transformers. You will not need your Y2 Annex D for this test. I have put questions in there that do not require the use of that table. So you will not be able to use your books for this. We're going to look at buck boost transformers. Buck boost transformers can be field connected as auto transformers to buck or boost the circuit voltage. They can also be used as an isolating or insulating transformer to provide low voltage power to control circuits or other loads such as lighting or nurse call stations, you name it. So these transformers are a smaller kVA transformer that are designed to be used in multiple fashions, whether it's an isolating or insulating fashion or a buck or boost fashion. When it comes to isolating transformers, remember these are dual voltage primary and dual voltage secondary transformers. You'll note that H4 and H3 is across from X1 and X2. Remember we talked about additive polarity. These windings in buck boost transformers are wound for additive polarity. Now, if I have a supply circuit that is lower of the two ratings, so again, let's say my rating on my buck boost transformer primary is 122/40. Each of these windings on the primary would not be rated for 240. They would only be rated at 120. And if I apply this to a single pole breaker, I would use diagram I here. Again, 120 each winding. If I applied it to a 240 breaker or a 2-pole breaker, each winding is still rated at 120, but I add them together by putting them in series in order to get my 240. You will need to know the relationship of series and parallel circuits for this exam. So test yourself. Go back and look at 224. I believe it's 1 or 2, and understand the principles involved with X1, X2 transformers like this. Not X1, X2, buck boost transformers like this when they're configured for a isolation configuration. None of these diagrams here are an auto transformer. These are all designed for isolation right here. These are isolation diagrams. If it were an auto transformer, there would be a connection between some of these circuits, between the H4 and X1, or between the H1 and X1. Depending on the configuration, there would be some sort of connection making this all one circuit. Sizing of buck boost transformers for boosting or bucking voltage. Your ICV, that means your input circuit voltage. Your OVR, that means your output voltage required. These formulas here will be used for the calculation of sizing buck boost transformers for either bucking or boosting. Note that the first one here is for when you're sizing it to boost, and the second one is when you're sizing it to buck. So if I have a transformer that is required to boost my rating from 208 to 230, my OVR would be 230, my input circuit voltage would be 208. Plug and play those numbers, multiply it by the kVA rating of the load, whether the kVA rating of the load is 50 kVA or 20 kVA or 10 kVA, doesn't matter. Just apply that number and you'll end up with your overall rating or kVA rating of your transformer. With buck boost transformers, smaller transformers rated 3 kVA or less are generally designed so that the secondary voltage is actually going to be slightly higher than the nameplate rating indicates. This is compensation. The reason being is oftentimes there's going to be a voltage drop under load. It means once the load is engaged, the volts are going to drop to compensate for the load. So to compensate for these volts lost, there's often a few extra windings added on the secondary side, or the turn ratio is changed just by 6%. 6% is what these are typically compensated by. So that means without a load attached to the secondary side of this transformer, I would have 6% more volts than the rating tells me I should. That being said, if I backfeed a transformer like this, I'll have 6% less volts through the backfeed. If I attach primary to my secondary and secondary to my primary, backfeed the transformer, expecting to get a higher voltage, I'll have actually 6% less than I anticipate. Buck boost transformer calculation and selection. Before I get into that, a little bonus for you. Extra credit number 1 on the test is letter C. The output voltage from a buck boost transformer depends on both the input voltage and the connection diagram used. So it means if I've got an output voltage I'm expecting, it's all going to be dependent on how much I need to boost it by, how much I'm applying to it. If I have a 208 volt circuit and I'm expecting to get 230, I'm going to use a transformer rated for that and use the diagrams rated for that. But however, if I use that same transformer and my the input voltage instead of 208 is more like 200, I'm going to have a less than expected output voltage. Again, with the whole turn ratio thing. Keep in mind that these transformers, again, are dual voltage primary and dual voltage secondary. So that means my H leads and my X leads can be either connected in series or in parallel. If I'm anticipating a higher voltage or needing a higher voltage, I connect them in series. If I'm anticipating or needing a lower voltage, I connect them in parallel. And then depending on whether they're bucking or boosting, I connect the sides according to the diagram. Again, you will not need your Y2 Annex D diagram at all. None of the questions will involve that today. Also, one other thing about buck-boost transformers. Again, just a reminder, when you're connecting these to boost or buck, they will be connected in an auto transformer configuration, meaning that both primary and secondary windings are connected together physically. For isolation or for low voltage transformer, these buck-boost transformers would be considered to be isolated because there is no physical connection between the primary and secondary windings. And for your information here, group 1, 2, and 3, out of your annex, these are your typical ratings of buck-boost transformers. You'll notice that the primary has a dual voltage rating of either 120 or 240, or 240 and 480. And then each group transformer has a dual voltage secondary. This is its dual voltage secondary if it were just an isolation of 12 or 24, 16 or 32, 24 or 48, meaning that each winding is rated for the lesser of the 2 volts per primary and per secondary. 14, or letter C. 226. Describe and explain the basic principles and purpose of standby generator sets. We're going to talk about standby systems, whether they're required, whether they're optional. Explain the installation, looking up the NEC references for them. Many businesses have standby generators installed to provide electric power if and when the utility power is not reliable, or to provide electric power when an emergency situation causes disruption of available utility power. If electric power is not reliable, then businesses can be interrupted, affecting safety, production, customer service, and employee morale. So standby generators, things that we need to talk about, things that you need to know for the test. These units have a fuel-propelled prime mover for propulsion. The prime mover is what turns the alternator to produce the electricity, or which turns the apparatus to get the alternator to produce the electricity. The NEC articles for emergency systems, legally required standby systems, optional standby systems, just general generator information are found here. I'd write these code references down. You will probably see one of these on a test, on the test, 1 or 2 even. Other things to consider for transformers, know your terminology. What's a day tank? How many hours is it supposed to supply fuel to the unit for? Know what an optional system is used for versus a legally required system. For healthcare, know your different categories. There will be some healthcare questions on this test. Most of it will be code lookup, but know your categories. Also, you're going to need to know some of your classified locations as well, from Article 500 through 505. Know your life safety, critical, and equipment branch circuits. You will have some questions regarding these life safety, critical, and equipment branch circuits. Know your code references there. And congratulations on making it through the end of this video. This video is intended not only for your attendance for tonight's class along with the in-house lab, but also for as a study guide for your midterm. Your midterm is next week, so take the material we discussed today, just go over it, go over your homework, go over your notes, make sure you have everything together. If you got questions, contact me, text me, email me. I'll get back to you as soon as I can. Other than that, the best of luck on your midterm, and I will see you when I see you next. Have a great day. Oh, by the way, just a small Easter egg for you. If you've continued to watch, hopefully you have, this will be for your benefit. Just a little freebie for you. Number 46 on the exam, letter A. And number 65, letter C. Best of luck to you.